So, hello everyone. So, we will continue with the topic evenness in textile material. Okay. So, now we will discuss the measurement techniques, measurement of evenness. So, first method is that by visual examination. So, if we can see properly, if we can see the material visually, so subjectively we can say this material is even or this is uneven. So, that visually we can judge. Okay. So, one is that lap meter. Lap meter, what is that? Here there will be one board which is from back side illuminated with light, okay, white. So, illuminating board, and over that we are placing our laps. Although laps are nowadays not being used in the industry, but and here in case of any unevenness, patchiness, it can show, because if we can control at that point, so that will give a direct indication whether this is going to create problem or not. Okay. So, that is a lap meter is one technique of measurement of evenness of lap by visual technique, and another is yarn appearance board. So, yarn appearance board is very actually widely used in industry, and this will give us very actually quick overall assessment of evenness of yarn. It is very simple technique, subjective measuring technique, provides important additional information that can be correlated with the appearance to the expected fabric made from a yarn. So, looking at the appearance in the appearance board, we can make out the what type of fabric it is going to produce. So, that it is very important, and very quickly we can measure, we can judge. Grading after viewing the sample of yarn wound on the designated traverse. So, the traversing will be there, there will be a black board on which the yarn is being wound. Okay. So, for colored yarn normally we do not use black board, in colored yarn it is a white board. On the white board we just wind the yarn, and depending on the count, the thickness of the yarn, the traverse rate changes. So, that proper distance, proper separation of yarns are there, and ASTM, as per ASTM there are 5 different grades, okay, and the board is compared with the standard photographs available, and we can grade them. Okay. Now, this is the typical yarn appearance board winder. This is the boards are of basically two types, one is the rectangular, another is trapezoid. So, this in this way, so we can simply wind the yarn, okay. This may be automatic or may be manual. So, that we can wind the yarn here and compare with the standard photograph, okay, available. Now, so grade A means best quality possible, okay. That means depending, it does not depend on the count, okay. It is basically overall grading. So, in that case there is no large naps, very few small naps, okay. No large naps, because why few small naps, because we are talking about the, say this is basically for cotton yarn, there will be some naps, short fibers will be there will be some naps. So, we cannot have the grade without any naps. So, there will be some naps, must have very good uniformity and less fuzziness, means hairiness is less, okay. And this is the grade A. If it is the our present yarn is close to this. So, that we have to judge subjectively. Okay. Similarly, little bit inferior than grade A is no large naps, few small naps, less than 3 small piece of foreign matters will be there, if it is, if at all it is there, slightly more irregular. So, irregularity will be little bit more, looking at the board one can make out, and fuzzy. So, it will be little bit hairy. So, that this is the grade B. So, if we can compare this, we can, and we have to place our board in actually beside this. So, we can compare which grade it is. Similarly, grade 3 will be little bit inferior. So, larger quantity of more naps will be there, higher fuzziness or foreign matters will be there. This is the grade C, and grade D is further inferior quality. So, in this way, so grade D is there and grade E below grade D. So, overall we can see, we can compare, we can place our board present here. So, we can grade accordingly. So, this will give us overall idea about the yarn quality. So, these are the different grade, we can see this is the best quality and this is the poor quality. Next is that the cutting and weighing method. This is very commonly used in industry. What we do? We have a material, yarn, sliver or roving, and we cut the material, okay, with certain known length L, so fixed length L. For yarn length is different, for sliver length is different, and for roving there will be different length, and even if you want to talk about the lap, it is different. Okay. So, that you cut this material and they then take mass M1, M2, M3, M4 like this, and we know the exact mass of the material of a certain length, and then we take the standard deviation and then CV percent, mean we know standard deviation, and then CV percent we can calculate standard deviation by mean into 100. So, this way we can calculate the CV percent of mass per unit length. Why I am telling the mass per unit length repeatedly here, it is important, because we will see in other automatic instrument we talk about the mass per unit length variation without measuring the mass, but here in cutting and weighing method we actually measure the mass. If you ask me the what is the value of average mass, then I should be able to tell that this is the value, this is the value of the average mass of the material x, okay, that value is available. So, that is why cutting and weighing method gives the exact value, exact reading, but main problem of this technique is it is a very slow technique. So, for day to day measurement or for large quick measurement it is not possible, and also cutting and weighing method, another problem is that our length cut is should be sufficient, so that we have certain mass. Suppose in this yarn, if we want to measure the mass variation of say per centimeter, 1 centimeter every 1 centimeter length, and we want to measure the CV percent, then it will be very difficult. First thing is that we have to cut a large quantity of large number of pieces, then we have to take mass, we have to take calculate mean, standard deviation, CV percent, then So, it is not possible, and if we want to have quick large number of sample, then it is impossible. So, cutting and weighing method is only possible when we have the smaller sample, we have time to measure, that in those case we can measure this. So, lab to lab variation. So, what we take the mass of lab and then measure the take the whole lab and then measure the mean and CV percent, that is a lab to lab variation. And lab meter is there where automatically 1 yard length is cut and then measured the mass of that 1 meter, and we can measure the CV percent standard deviation. The weights are recorded subsequently and data analysis is there. Now, for sliver, roving and yarn, still it is being used, because we need to know the exact value, because we need to calculate the count or linear density, because we not only serves the unevenness measurement, evenness measurement, it also measured, we by that we can measure the actual linear density of the material. That is why here the count or Hank and CV percent are checked. So, here CV percent along with the count or count along with the CV percent is measured by measuring a test length and then weighing it accurate by balance. Okay. So, for sliver, it is the length specified is 6 yard length, we can take more than 6 yard, but then in that case it cannot be compared. So, if we want to compare the CV percent of one material to another material, so in that case we have to keep the length fixed, otherwise if we increase the length, then the another type of problem will crop up, that I will discuss, which is called VL and PL, between length variation and within length variation, that I will discuss in detail. So, in that is why we need to compare the uniformity or irregularity at for a particular specified length. So, for sliver 6 yard is the standard length. So, and we actually measure this length by wrap block, and for roving it is a 15 yard is standard, again we use the same wrap block, and for yarn it is 120 yards we use wrap reel, that we have discussed already when we discussed in the yarn count measurement. Next technique is by measuring the variation in thickness. Okay. So, this material, suppose this is sliver, here the sliver thickness, that if we measure the thickness of the sliver at different portion, that will give the idea, indirect idea of mass variation. There are various techniques of measuring the thickness variation. By measuring thickness variation, we can measure the irregularity of material. So, one of them is that it is called groove and shoe principle. This is actually used for sliver or relatively soft material, where number of fibers in the cross section is large, because it cannot, it is not possible to measure like roving or thinner material. Here the sensitivity of the instrument is not that fine. So, that larger variation it can measure. So, the principle is, I will just draw here, this is a groove. Okay, this is a groove. Here in the groove we are passing the sliver material. Okay. Now, I will draw with other color. So, this is material and this one is groove. Okay. And now, what we are placing? We are placing one shoe. That is why it is called groove and shoe principle. Here this is providing some mass weight, and this distance, this is the thickness, we are measuring the thickness. Okay. And if I draw the side view of this, okay, this is the contour, and now here it is a, this shoe is okay. Now, and the material which is moving. It is moving. As this material is moving, this shoe will have this type of motion, which is actually measuring the thickness, upward motion. Okay. This type of and this indirectly, this we can record. If we can record this movement, we will actually, it is giving the unevenness of material. Okay. This is one principle. This principle is known as the groove and shoe principle. Now, another technique is here. This technique is known as the WIRA, Wira roving levelness tester. Okay. This is used for either roving or sliver soft material. The principle wise it is almost similar to the this other technique, the groove and shoe principle, but here the recording is better. Okay. Now, and this Wira roving levelness tester, the principle wise I can just draw. Here the roller which is motor driven roller, okay, and this is a driven roller, motor driven, okay, A, and here it is a flanged top roller with a flange. So, top roller I am drawing with a red color, top roller, and which is flanged. Okay. And material moves through this, in between this. This material is moving. Okay. And for this any unevenness, this roller will move up and down, but the in this instrument the arrangement is there, we have to record this. This movement is very small, because the roving thickness, if we see the actual roving, this is the type material. Here even if we talk about the variation in thickness, and this deflection will be very small. Now, mechanically this can be actually amplified. This is amplified by this arrangement here, it is a pivoted here and this is okay. Here it is pivoted here, and this deflection, whatever this deflection here, this will get magnified here. This is once it is magnified, it is now this movement is actually by the due to the variation in thickness, okay, and it is moving. And now from here we can record the this thickness variation, and the thickness variation is recorded by, this is a connector here, another arrangement is at this point, I will draw with the other color, this is the connector, and here what we have? We have this is fulcrum at this point. Now, this portion is moving up and down, this portion will move up and down, this is moving up and down, this will also move up and down depending on that, this is fulcrum here. Now, from here there is a connector here, and this is actually driving connecting with the another system, and this system it is a L shaped and which is pivoted at this point. This is on rod, okay, L shaped link. I can just draw this is the separate link. Now, here we have different points, we can shift it. Now, thing is that now as it is moving up and down, this will also move up and down as it is connected here. If it is moving up and down, this will move up and down, okay, the sideway, this will make sideway movement, and with this there is a link, and here it is a PN recorder, PN is there. This is the pen and a chart is moving, chart is continuously moving, and pen will make lateral movement, which is nothing but the variation in the thickness, and the chart as chart is moving. So, this will give this type of motion. So, this is actually nothing but the diagram, this is giving the variation in the material, okay, variation in thickness of the material, and if we know the distance, exact distance, if we and this link arrangement, we can calculate the exact thickness variation from this curve. And the magnification, suppose we have a finer material, we have sliver, we have finer material. In case of finer material, what we will have? Our variation in thickness will be very small, variation in thickness will be very small. So, that we have to actually amplify. So, this way we can, what we can do here, there are different connector here, we can change, we can shift the connector, then if we shift the connector to from this to this, then this will get more deflection. So, higher deflection, the deflection we can change by resetting everything. So, this instrument it gives the variation in terms of thickness variation. So, thickness variation we can measure by groove and shoe method or by Oira levelness tester. There are other techniques also which use the thickness under compression. One is that Anderson yarn tester. Anderson yarn tester, it's actually the principle is exactly same. Here the yarn is tested, it is not the compressible material. Here the yarn is little bit harder material, whatever the thickness variation is there, that will get actually that is measured here. This the recording of yarn thickness variation taken from optical arrangement. Here actually by using light reflection one can measure the yarn thickness variation. The reflected light beam falls on a strip of moving photographic plate. Okay. So, photographic plate is moving and reflected light, pointed light is actually projected on that and trace is generated. Okay. And this is the technique here. here this is a shoe and this is anvil, the yarn is moving and it is connected with this. Okay. Here it is a, this is the pivot point and just over that there will be one mirror and ray of light is actually falling on it, and here it is a photographic plate will be there, and as the yarn thickness changes, this mirror will get tilted, okay, depending on the thickness, and this ray as it is fixed ray, this ray will move, okay. There will be a movement of this ray and this movement is proportional to the thickness variation. So, that is the principle of Anderson yarn tester. Another measurement is the by using compression, it is the yarn diameter actually tester, roller yarn diameter tester. It is a simple tester where this is the yarn, this is the there are different rollers are there and yarn is moving on this depending on the diameter variation, and this anvil will move up and down, and this can be recorded by using micrometer or maybe by electronic arrangement. We can directly measure this thickness variation. Now, next is that most important, which is very widely used, the it works on capacitance principle. Now, in capacitance principle, the principle here is that the material moves through slot, and slot is between a two capacitor plate. Okay. Now, this capacitor plate is it is an indirect method of measuring the change in mass per unit area, which is very important, which we should remember. So, in other methods as we have discussed, those are the direct method. In capacitance method, although it is very widely used, but here the method of measurement is totally indirect. Now, these are the capacitance plate, capacitor plate. Now, if the and it has got certain dielectric constant. Okay. Now, when once the material is there in between, material is there, this the mass presence of material, quantity of material, it is not volume, not so volume, it is the quantity of material which actually changes the capacitance of this plate. So, the quantity is basically nothing but the mass of material, okay, and the capacitance is proportional to the mass of material changing. So, capacitance it is not change, it is a capacitance of the material of this capacitor is proportional to the mass. If mass changes, then capacitance change. That means, are we measuring mass? No, we are not measuring mass. We are measuring certain value of capacitance value, which we know it is a proportional to the mass of the material. We are not from this instrument, the negative point is that from this principle we cannot get the value actual count of the yarn, we cannot get the actual mass per unit length of the yarn, x bar we cannot get, although we get the variation. This is the, but variation we want. So, this instrument, this capacitance principle, although it measures the variability in terms of mass per unit length, but it is only limited to that. So, this instrument it is not expect, we cannot expect to give the value of mass per unit length, it will not give, it will only give the variation. So, because capacitance is actually it is proportional to mass. So, K m, this K value is unknown, K value is unknown, K depends on various factors, it depends on the material, depends on the moisture content, depends on many things, the twist level depend on the. So, K for a material, for a yarn, for a particular yarn, for tested under particular condition, particular Tm, particular fiber, K is constant. So, with that assumption we can measure only the variability. I will just come, and the yarn is passed through the parallel plate capacitor in continuous fashion. Okay. And one thing is important, the its indirect method of measuring the change in mass per unit length. So, what is the unit length? Now, so this is the capacitor plate, and through which our material is passing, yarn or sloving, and this is passing through this, and the length of the capacitor plate is this, and normally in normal evenness tester it is typically 1 centimeter. That means, at any instance the value, so this it is moving at speed of v, the value which the C is getting, which is proportional to the mass, this mass of this quantity of yarn within this is the quantity. What is this quantity? Length. The length here is this much length. The C is not taking care of any length, any yarn which is beyond this, it is not taking care of. It is only concerned with the yarn which is within this zone, and this condition here is that yarn is the whatever yarn roving or sliver, they are in straight moving at straight line. That means, the length between this, it is a 1 centimeter length, which is a unit length, and this mass of 1 centimeter, that means the C is proportional to the mass of this quantity. Now, how is it taking then C of next value? So, C 1 is that this portion, this is portion 1. Now, as it is moving continuous, suppose now let me draw once again, this is the capacitor's plate, and then the material is moving, this is the material at moving at known speed v. Now, here this is say 1 centimeter, this is actually measuring the capacitance for this mass. Okay. So, K m 1, this is 1 unit 1. Now, next it should take the mass of this unit. Okay. Now, how will it take? So, it has certain speed. Now, by that speed, after certain time delta t, this portion will reach here. Now, the delta t is the frequency, that is the time interval for the next reading, that is automatically adjusted. So, for next reading what it will do? It will not take the data of this overlap portion, it will take data of the next portion. So, that we can adjust, or maybe after certain distance, okay, any distance after that. And but once it is taking the data, the software it is sending the signal, capacitance signal, that signal is actually the mass proportional to the mass of 1 centimeter, that is the length of the capacitor. So, that mass is say m 2, k m 2, k m 1, k m 2, k m 3. In this way it will keep on sending the data, and large number of data C 1, C 2, C 3, it is only giving the value of C, some electrical signal, but we know that value is proportional to the mass value of that. Okay. Now, we have not yet got the exact value of mass. Okay. We have got only the proportional of mass. That is why here we are talking about only change in capacitance. Okay. Electron, we are talking about the variability of the material. Now, this is the principle here, it is a measuring head, and here the length is 1 centimeter as I have mentioned here, and signal processing, display unit, recording unit, printer, everything is there. And then a change in mass of the dielectric, okay, change in mass of the dielectric material, like in our case it is a yarn, non-conductive yarn material. In the condenser changes its capacitance. So, capacitance is changing, which is proportional to the mass of the material. Okay. So, K m is their capacitance, and if the material is drawn at a constant speed through the condenser continuously, the change in capacitance will follow the variation in mass per unit length, that I have already mentioned, and the unit length being here, it is the length of the capacitor. For this Wooster tester, it is a, for norm most of the witness tester, it is a 1 centimeter. Okay. And also one thing one should remember here, once we are getting the data of consecutive 1 centimeter, okay, once we are getting the data of consecutive 1 Km1, Km2, Km3. Now, if I want to measure, now what we will do, we will measure the variability in terms of CV percent or percentage mean deviation, and we will see if we measure the CV percent or percentage mean deviation, the as we will be dividing with the mean standard deviation, as we will be dividing standard deviation with mean or mean deviation with mean. So, in that case you will see standard deviation will be proportional to k multiplied by something, and mean will be k multiplied by something. So, this k will get cancelled out in both the cases. As k is getting cancelled out, so we do not have any problem whether it is a mass variation or capacitance variation or any electrical signal variation, it is giving the exactly same data, because we are talking about the only the variation. So, this type of instruments, indirect measurement will only give the variability in terms of CV percent or in terms of PMD, percent mean deviation, where the constant factor gets cancelled out, we are getting actual variation. Okay. Now, here it is a 1 centimeter length. So, now can we get in using this instrument, can we get the variation? So, the percentage mean. So, now let me tell you one important, I can explain one important phenomena in this instrument. Suppose this instrument it is working running at the speed of say 400 meter per minute, okay, 400 meter per minute, and this 400 meter per minute. So, for it is running for 1 minute, and using this instrument, suppose we have got one U percent or CV percent. The percent wise it is exactly giving the value of M1, M2, M3. Now, if I ask you, I will give you the yarn is for 1 meter it is tested. So, it is a 400 meter is being tested, okay, through this capacitance plate, okay, through this capacitor. So, the total length of yarn is 400 meter, and I have got one value. So, for U percent I have got say 10% U percent, this in yarn has got U percent of 10. Okay. Now, I am telling you I will give you the same portion. So, 400 meter is tested, I have collected the 400 meter in a bobbin properly kept and I am giving you the yarn, can you calculate u percent without using this machine in this instrument, only using the cutting and weighing method and reaching to this value? It is possible, it is possible. First thing we must know what is the this length of the capacitor. Now, length of the capacitor we know it is a 1 centimeter. Now, 1 centimeter. Now, this total 400 meter yarn, what I will do? I will cut in 1 centimeter length each. So, how many the such pieces will be there? In 1 meter there will be 100 pieces and 400 meter we will have 40,000 pieces of such masses. I am talking about theoretically. So, it will be M1, M2, M3, M4 like M40,000. Then 40,000 small pieces I will take, what I will do? I will take the mass of individual M1 by weighing in a microbalance. Then we have the real data, then I will what I will do? I will measure the mean deviation using the formula, then I will measure the percentage mean deviation and I should get the value 10%. So, that is why this say, although this will give us the value theoretically, but it is practically not possible. We will get exactly same value using the indirect technique of measurement and that too within 1 minute, and value wise it is exactly same. Only difference is that in this process, in my process of measurement, I can tell the yarn is, the count of the yarn is 30 ticks, because I know I have the value of the mass per unit length, but here it will not give the exact value. Okay, that is, but it will serve its purpose, because this technique is not for measurement the yarn count, the technique is the measure for the measurement the variability of yarn. Okay. That is the basic concept we must know, and also this instrument not only give the variation in 1 centimeter, although 1 centimeter is the minimum length, we can an unit length, we can have variability of any cut length. So, u percent is the variability of the cut length. What is the cut length? Here cut length is 1 centimeter. If I want to measure the variability of 10 centimeter cut length, its machine has done its function. Now, the thing is the software function. What software will do? Software will only add the this capacitance value of first 10. So, k M1 plus M2 up to 10 M10, that will be for 10 centimeter, then k M11 M20 second reading. So, in this way it will give. So, instead of 1 centimeter, suppose it was getting 40,000 reading, if we try to increase the length, then it will get the value, number of value will be less. So, in this way we can get at different cut length, it will give the unevenness value. Okay. And next is that unit length here is 1 centimeter. Now, try to see here, if the material is drawn at constant speed through the condenser continuously, the change in capacitance will follow the variation of mass per unit length. So, its capacitance change, its actually its exactly it will follow the mass per unit length variation. Now, how to calculate the then u percent from this curve? Here this is the variation in mass per unit length, as all actually you are getting the capacitance value, only thing it is a factor of k. So, factor of k we know, and this is the A. A means area of this shaded portion. If we know the mean value, now the mean is another problem. Now, how does the instrument know the mean value? You must, if you see the Wooster or any evenness tester carefully, once it is started, the instrument is started, the screen it remains blank, and during initial few seconds it tries to actually get the data of mean capacitance value, and then once it gets the mean capacitance value based on large number of initial data, it plots the this type of curve. This is the mean value, okay. Mean value of this apparent mean value, then accordingly it keeps on plotting. Now, the thing is that suppose there is a yarn, initially it is a thin yarn, and after that it has got say actual yarn, thin by some mistake, okay, initial portion thin yarn. Now, if we test this yarn in say Wooster machine or any evenness tester, suppose this yarn is moving like this in the capacitance tester, it is moving. So, within the initial length it has actually gauged the mean value. So, this has been plotted. So, this is immediately plotted within few seconds. So, by that time it was moving. So, then it is started actual plotting, up to this point it is plotted, then you will see suddenly it has increased. This type of plots are possible. This shows there is a major problem in the yarn, suddenly you will find suddenly it is coming out. So, this plot is known as diagram. Diagram I will just explain, it tells many things which no other plot gives, even the spectrogram. Okay, I will just explain. Now, area under the curve, what is that? Area under the curve? Area under the curve, this is A, which is nothing but the summation of the mean deviation, that deviation of from the mean. So, this if you keep on adding, this is the mean and this deviation, the x minus x bar, this x is the mean, this is the summation of deviation from mean, and it's taken the mod value. So, this is the actual area. So, if you talk about this and that divided by the t value, okay, that is by the number of read t. What does it does? T means t shows the number of readings are taken. T is with the time, this is the time axis, but this time is proportional to the number of reading. Okay. Now, this t, this divided by t number of reading, it is called the mean deviation. So, what we are getting, we measure the area and then divided by number of reading, that is proportional to t, that gives the mean deviation. If we divide it by x, that is the mean value, that will be, and multiplied by 100, it is giving the mass, actually the u percent. Now, here it is interesting, here if we see this x and x bar, it has got a component of k, that is it is giving the actually it is a capacitance value, it has got the component of a k. If we take out the k outside, then this will be the m value, mass, okay. and this k value, and here also its k is there with that x value, mean value. So, this k will get cancelled out. So, ultimately it is basically if we take the u percent of percentage mean deviation of capacitance value and percentage mean deviation of mass value, the meaning the actual value will be same, actual numerically it is same. Okay. Similarly, coefficient of variation is also coefficient of variation, it is the deviation in standard and then under root. Okay. That is the standard deviation divided by mean is the standard deviation we can write in this form, and this is the mean, and here also it is the k value gets cancelled out. And for normal distribution we have seen CV is related with mu u value, it is by 1.25 times. Now, coming to one of the most important graph picture which gives the diagram. So, the graphical representation of mass per unit length variation along the length of sliver, roving or yarn is reflected as diagram. It indicates the nature of variability present in the material. Now, this is a one diagram. Okay. Now, another yarn is having diagram like this. From this, looking at this diagram, we can make out which one is more even. Clearly, we can see that this yarn red, it gives poorer actually evenness. Okay. This yarn green, it is even. So, similarly, in this picture, this diagram, okay, diagram this one, it is even yarn, although there is a variation, it is even, but this yarn 2, this one bottom, it gives very high variation, it is not that even. Okay. Next is that we get the a large number of information, large very wide information from the just simply looking at the diagram, which we cannot get, like long wavelength variation, even with periodic variation which spectrogram cannot give, like the yarn is there. Spectrogram only gives the variation which is repeating several times. Suppose we are testing 400 meters of yarn in 1 meter. If it repeats minimum say 6 to 8 times or 10 times, then only spectrogram will show there is a variation, because spectrogram amplitude vertical, that axis x axis, it is a basically it is a histogram placed very close to each other, and that vertical the height, it is nothing but the number of times the fault gets repeated. If it repeats only once, the spectrogram will not show, but if we see very carefully the diagram. So, this is suppose total length is 400 meter, very long length. Okay. Now, if the diagram is like this, this is the diagram. Now, this diagram if we see the diagram carefully of the total length of the yarn, this will give there is a very long wavelength, longer wavelength, and its periodic variation, and this variation, this type of periodicity that the spectrogram will never show, and we can see the nature of the wave and we can analyze this. Another variation is that suppose the yarn is running, it is moving perfectly, it is testing, it is going on. Suddenly in draw frame somewhere there was some double sliver came, extra sliver came there, and it is reflected, and that was for longer length. It will not reflect in any other picture, but in that case diagram will show like this for say hundreds of meters, then suddenly it. So, this type of sudden change in mean value will be shown in diagram only, not with other type of management. Okay. So, long variation, even with the periodic variation which spectrogram cannot confirm. Spectrogram will give some idea, but it cannot confirm. Extreme thin or thick places, as I have just shown, extreme thick places it will show, it is a very high thick place, and that even in other data we cannot get. Only visually the diagram will tell the yarn has got extreme thin place or extreme thick place, sudden change in thick place. So, changes and step changes in the mean value. So, mean value has suddenly stepped up or stepped down. So, all these variations we cannot get from other method of measurement. Okay. In many cases it can confirm the numerical value of the instrument. So, looking at this value, looking at the type of the graph, like I will show last one. Now, here this two yarns are there, definitely this yarn will give higher U percentage. So, that numerically by without looking at the data, if we have this values, this value, this is very useful. Data is actually that particular value, it is dependent on various factors, but if we see the diagram we can make out, okay, this yarn is very good, we can go for this yarn, okay, this is inferior quality. So, it can actually confirm the numerical value. Okay. And we will stop here. In next class we will continue with this, with there are various ways of expressing the unevenness. Okay. Thank you.